Okay, so for PLC applications, we're going to connect our PLC up to our VFD. We've got a GS1 drive and a Siemens 1215C PLC, and we're going to physically connect them up. And Advanced PLC will do the logic to make this work. So when you come in, the PLC will already work the way it should. So if you're taking Advanced PLC, you'll be working on that aspect of it. In PLC application, we're going to make it work on the physical aspect. There's a couple of things that you need to know about how our particular PLC works. So our inputs expect a 0 to 10 volt signal. Our outputs are going to put out a 0 to 20 milliamp signal. Okay, so over on our drive, we've got a little switch. It's in the up position right now because we were reading voltage. We want to put it into the down position because we are going to be reading current. So the first thing you want to do is make sure to change that. All right, on our drive, we've got a 10 volt output. We've got a analog input. We've got a common. Okay. The way we've got it set up right now for the speed of that drive, we've got it set up so it's coming out of the 10 volts, running through the little potentiometer, and then the wiper of that potentiometer is going to the analog input, and the common is going to the other side of the potentiometer. What this does is it makes a voltage divider that we can adjust where that middle voltage is. Okay. Now we can do a lot with this. We have it set up so whatever position we put that knob in, the GS1 will speed up the motor to that point. By programming that acceleration and deceleration speed. So as we change it, it'll take that amount of time. Right now we've got it set up for 5 seconds for acceleration and 10 seconds for deceleration. And there's a whole lot that we can do with the drive. But in the bigger scheme of things, I like programming the PLC better than I like programming the drive. Because what I can do is I can make the drive a lot dumber and say, hey, just do exactly what I tell you to. Don't worry about these curves or don't worry about anything else. And I can commission these drives systematically so that they're, always the same way. And then I can change those parameters in the PLC. And that's a lot easier to do through the network. It's a lot easier to do programmatically. So I can just go in and change a variable here or there in the program, as opposed to having to go through the screen on the GS1 and change those for the different use cases. Okay. All right. So let's look over in the right-hand corner of the PLC. We'll have a common. It's got an M on it, but it says 2 because it's a separate common. We'll talk about that in a minute. We've got input 1 and input 2, which is starting at 0. So those are our outputs. So we'll put an AQ. The Germans like to use Q for output, so we don't get confused with the O and a 0. All right, so this little terminal block right here is going to be your analog ins and outs. The first 3 are for your outputs. Let's make this a little bit bigger. You got a 3M and a 0 and a 1 for your analog inputs. So if we're reading something in a PLC, the input is going to light up a little LED in there. Okay. So if we put, well, on the analog it's not, but for the digital it will, and it'll make more sense if I show it this way. If I just attach a voltage up here, we don't have current going through the LED. We need to return it back to the same source that we came from, so that we make an actual current loop. Okay. So there might be a bunch of different power supplies that we're using for different things. You'll return your common back to whatever the power supply is that is, supplying the voltage that we're going to be using. Okay. So we're going to take this common off of here, and we're going to take this analog input. We're going to come back to it in a minute. Okay. Now, we still want to use that 10 volts. We could take the 24 volts off of here, the 24 out, put it through a resistor to drop it down, and then would drop down 14 volts so that would have 10 volts on the top of that resistor. And we do that a whole bunch. Okay. So, we can do that, but since we have a 10 volts just sitting there, what we're going to do is we're going to let that 10 volts be our power supply for our analog input. Okay. Then instead of going directly to the drive, we're actually going to go to the analog input number 1, which is 0.0. Okay. All right. We also need to tie this common to here. Let's go ahead and let's doctor this up a little bit. Let's set the wipers down here. Okay. This will just make the drawing a little bit easier. All right, so we're going to take the middle terminal of that potentiometer, and we're going to go to the first input of our analog input. All right, now the analog input of here does not know what we're referencing, so we're going to have to tie it back to that common so it has a frame of reference. Okay. We're also going to have to tie this side of the potentiometer, and I'm putting a dot here to represent that we're going to be tying those together, okay, to the common as well. All right. Now, let me change colors real quick. We're going to take this analog output. Notice I didn't put a dot there because I'm not connecting the wires. They're just crossing over each other. I want to take the analog output, the first one, and put it into the analog input of the drive. All right. Now, the couple of ways to do this, I'm going to do just a different color. I need to tie that common to those other commons as well. Okay, because they're all using the same frame of reference. All right, now there's a lot of ways of skinning this cat. Like, you probably don't want a bunch of wires that are super long. You notice this right here, these two wires, they don't have to be that long. Like, instead of tying it back somewhere in the middle or wherever, I can jumper these two commons right here. All right, so I take a wire and I put it in between the 2M and the 3M. And since this black wire right here is connected to the common over here, they're both connected. That's going to save me some wire. Okay. You know, think of it like a puzzle. Like, how can I, you know, how can I use the shortest amount of wire? Think of that. But you need to electrically make these connections. All right, notice that this pink wire is not connected to that blue wire. That blue wire is my analog output of my PLC going into my analog input of my VFD. Okay. Now everything else is going to stay the same. Like, we've got the drive set up so that we've got a forward and a reverse switch that we can turn back and forth. We've got it set up so that we've got a push button so we can start it, and we've got a normally closed push button so we can stop it. All right, those are going to stay wired up to the drive the same way. Okay, I'll throw this on the screen. This is more for PLC applications instead of advanced, but we're going to do the program aspect of it in advanced, and get it set up for them so that when they wire this up, does that show up on the screen? So I was just explaining how the wiring actually works to get the PLC to control the drive. It's a potentiometer. So a potentiometer is a resistor with a wiper, and so that wiper makes a variable voltage divider. So if we had 10 volts up here, 0 volts down here, depending on where we turn that knob, would have 0 to 10 volts. Yeah, it's exactly what that is. So we'll go through, you'll rewire this, okay? And now, whenever you're doing wiring, you need to verify that the power is off, okay? So you'll do this with that breaker off, tag that out, and then when you open that door, when you open it, it kills that door disconnect. So verify that the power is off before you start making these connections. That big switch that you use to unlock the door actually breaks the circuit, but there's still power on the top of that breaker or that disconnect. So we're killing it way over. Yes. All right. So for my advanced students, y'all have it set up like this. So I want it set up all the time. So when you get done with this, leave it so that if advanced comes in, they can program what we're going to program in advance and have it set up so they can test it. But don't use other people's work. Take off the wires and then redo it so that you get to verify that this actually works. Okay. So when my advanced students put stuff in, they're going to leave it up so you'll be able to test it on the physical level where they're testing on the logical level. Okay. So wire this in. What this will do is it'll put the PLC in the chain instead of directly telling the drive what to do. You can make the drive kind of ignorant. You can take out a lot of parameters in there, save a lot of time on programming the drive, because it's a lot easier to do some of the things that we're going to do with the PLC instead of sitting there and trying to program everything through the little keypad on the drive. We'll just tell the drive what the motor is and to listen to this input that the PLC is putting out. And the PLC will take care of all the heavy lifting as far as like trying to think about what things should be. Okay. So that should get you where we want you right now. All right. So we're going to interface this PLC through the analog outputs to the drive, but we're also interfacing this potentiometer to the analog input so we can change what we want. We can tell the PLC what we want it to do at runtime. Okay. Like we could tell the drive to go 100% full speed and ignore this knob. Or let's say that if we wire up that potentiometer straight to the drive, would have a range of 0 to 60 hertz or 0 to 3,000 RPM. Our operator might not know what is a good speed for us. Like there could be a speed that we don't want them to go up to, and the operator's looking at it like, oh well, if I go up double the speed, I can get out double the parts. But we might not convey the information to them that at a certain point, if you're getting half of your product destroyed because the machine is too fast, or something of that nature, that they might not need the potential to go up to a certain speed. Or like if we wire it up straight to the drive, would have the full range of the speed, and the working range of that machine might only be from 30 hertz to 50 hertz, or a certain rotational RPM that we want that machine to be going at, and they should only be able to tweak it a little bit, like speed it up a little bit if it's good, or slow it down if it's starting to do whatever, and they don't need that full range. So we might take the full range of that potentiometer, which would be 0 to 10 volts, and if we went straight to the drive, we could go from 0 to 3,000 RPM. Well, by putting the PLC in the middle, we could change what the operator is actually able to do. Like instead of taking it all the way down to nothing or all the way up to full speed, we could look at it and say that the optimal range for that would be 2 to 2.5k RPM. And no matter what he does with this knob, that knob would be in the range of 2 to 2.5 RPM or 1,000 RPM. And nothing that the operator could do at the operator station could change that. So we have a lot more power by letting the PLC do these decisions for us instead of just letting the operator go, okay, well, I'm lazy today, I'm going to slow it down a little bit more. Or, they turn it full speed and they're getting half the product messed up. And that's not a good thing either. So that should give you enough for what I want done this week. Y'all have a good